According to National Electrical Code Section 225.32, which addresses outside feeders serving multiple buildings or structures, a readily accessible disconnecting means is mandatory at the point where the feeder enters the building. This requirement ensures that the feeder can be quickly de-energized in case of an emergency or for maintenance purposes. However, there are exceptions to this rule. Exception number 1 states that a disconnecting means is not required for feeders supplying single-phase dwelling units or small non-commercial buildings under specific conditions. These conditions include the feeder being protected by an overcurrent device located on the premises of the building being served. Additionally, the feeder must either be run underground, be installed in a raceway and not enter the building for more than 25 feet, or have a disconnecting means for the building located adjacent and readily accessible from the feeder's entry point. Now, considering the given scenario involving a hospital with multiple buildings and a feeder running from one building's main switchboard to a distribution panel in another, it's essential to assess whether exception number 1 applies. Given that a hospital does not fall under the category of a single-phase dwelling unit or a small non-commercial building, exception number 1 is not applicable in this situation. Consequently, a disconnecting means is indeed required at the point of entry of the feeder into the second building. The National Electrical Code provides flexibility regarding the precise location of this disconnecting means. It simply mandates that it be readily accessible. This means the disconnecting means can be situated either within the distribution panel itself or externally, such as in a meter socket or a dedicated disconnect switch positioned outside the building. Considering the hospital's operational context, where it functions under a single management structure and adheres to a safe switching procedure, there's a reasonable likelihood that the disconnecting means could be conveniently located within the distribution panel. This arrangement could streamline operations and maintenance activities while still ensuring compliance with safety regulations. However, to ensure the most appropriate and code-compliant solution, it is highly advisable that the hospital consult with a qualified electrician. The electrician can assess the specific installation conditions, taking into account factors such as accessibility, safety protocols, and local regulations to determine the optimal location for the disconnecting means. This collaborative approach will ensure that the installation not only meets the requirements of the National Electrical Code but also aligns with the hospital's operational needs and safety standard. When selecting a disconnecting means, several factors should be considered to ensure it meets the requirements of the National Electrical Code and the specific needs of the installation. Firstly, the disconnecting means must be readily accessible. This means it should be located in a place where it can be easily reached without the need for tools, ladders, or other equipment. The disconnecting means should also be clearly labeled to indicate its purpose. This will help to ensure that it is used correctly in an emergency or during maintenance. Secondly, the disconnecting means must be rated for the voltage and current of the feeder. This is important to ensure that it can safely interrupt the flow of electricity in the event of a fault. The disconnecting means should also be listed by a qualified testing laboratory such as Underwriters Laboratories or Intertek. Thirdly, the disconnecting means must be suitable for the environment in which it is installed. If it is installed outdoors, it must be weatherproof. If it is installed in a hazardous location, it must be explosion-proof. Fourthly, the disconnecting means must be installed in accordance with the National Electrical Code and the manufacturer's instructions. This is important to ensure that it is installed safely and correctly. The National Electrical Code provides specific requirements for the installation of disconnecting means. For example, Section 230.71 requires that the disconnecting means for a building be located at a readily accessible point nearest the entrance of the service conductors. Section 225.39 provides requirements for the type of disconnecting means. Some common types of disconnecting means include circuit breakers, fused disconnect switches, and non-fused disconnect switches. Circuit breakers are commonly used as disconnecting means because they provide both overcurrent protection and disconnecting means in a single device. Fused disconnect switches provide overcurrent protection and disconnecting means in a separate device. Non-fused disconnect switches are used only as a disconnecting means. The selection of the appropriate type of disconnecting means will depend on the specific application and the requirements of the National Electrical Code. In summary, when installing a feeder to a separate building, it is important to understand the requirements of the National Electrical Code Section 225.32. A disconnecting means is required at the point of entrance of the feeder, unless an exception applies. The disconnecting means must be readily accessible, rated for the voltage and current of the feeder, and suitable for the environment in which it is installed. It must also be installed in accordance with the National Electrical Code and the manufacturer's instructions. Consulting with a qualified electrician will help ensure that the installation meets all applicable requirements. Let's delve a bit deeper into the considerations for locating the disconnecting means, whether inside the distribution panel or externally. Placing the disconnecting means within the distribution panel offers several advantages. Firstly, it consolidates the electrical equipment, making it easier to manage and maintain. Secondly, it provides a more aesthetically pleasing installation, as the disconnecting means is concealed within the panel enclosure. Thirdly, it can potentially reduce installation costs, as it eliminates the need for additional enclosures and wiring. However, there are also some potential disadvantages to consider. Firstly, the distribution panel may not have enough space to accommodate the disconnecting means. This is especially true in older installations or where the panel is already crowded with other equipment. Secondly, the disconnecting means may be less accessible if it is located within the panel. This could be a concern in an emergency situation or during maintenance. Thirdly, the heat generated by the disconnecting means could potentially affect the other equipment within the panel. Locating the disconnecting means externally, such as an ammeter socket or a disconnect switch, also has its own set of advantages and disadvantages. One advantage is that it can provide a more accessible disconnecting means, especially in an emergency situation. Another advantage is that it can be easier to install, especially in situations where the distribution panel is already crowded. However, there are also some potential disadvantages to consider. Firstly, an external disconnecting means can be more vulnerable to damage from the elements or from vandalism. Secondly, it can be less aesthetically pleasing than a disconnecting means located within the distribution panel. Thirdly, it can potentially increase installation costs as it requires additional enclosures and wiring. Ultimately, the decision of where to locate the disconnecting means will depend on the specific circumstances of the installation. The hospital should carefully consider all of the factors involved and consult with a qualified electrician to determine the best solution. The electrician can assess the available space, the accessibility requirements, the environmental conditions, and the budget to recommend the most appropriate location for the disconnecting means. Furthermore, the electrician can ensure that the installation complies with all applicable codes and standards. Now, let's elaborate on the various types of disconnecting means that can be used for this application. Circuit breakers are a popular choice for disconnecting means due to their dual functionality as both overcurrent protection and a disconnecting device. They are available in a wide range of sizes and ratings to accommodate various feeder sizes and voltage levels. Circuit breakers offer the advantage of being resettable, meaning that they can be easily restored to service after a fault has been cleared. Fuse disconnect switches provide overcurrent protection and disconnecting means in separate devices. They consist of a switch that is used to disconnect the circuit and fuses that provide overcurrent protection. Fuse disconnect switches are a reliable and cost-effective option for disconnecting means. However, they require the replacement of fuses after a fault, which can be time-consuming and inconvenient. Non-fuse disconnect switches are used solely as a disconnecting means. They do not provide overcurrent protection and must be used in conjunction with a separate overcurrent protective device such as a circuit breaker or fuses. Non-fuse disconnect switches are typically used in applications where overcurrent protection is already provided or where it is not required. The selection of the appropriate type of disconnecting means will depend on the specific application and the requirements of the National Electrical Code. Factors to consider include the size and rating of the feeder, the available space, the environmental conditions, and the budget. The National Electrical Code provides specific requirements for the selection and installation of disconnecting means. Section 225.39 specifies the types of disconnecting means that are permitted for use in feeder applications. Section 230.71 requires that the disconnecting means for a building be located at a readily accessible point nearest the entrance of the service conductors. It is important to consult with a qualified electrician to ensure that the disconnecting means is selected and installed in accordance with all applicable codes and standards. In addition to the above considerations, it is also important to ensure that the disconnecting means is properly maintained. This includes regularly inspecting the disconnecting means for signs of damage or wear and tear. Any damaged or worn part should be replaced immediately. The disconnecting means should also be tested periodically to ensure that it is functioning properly. The testing should be performed by a qualified electrician. Proper maintenance of the disconnecting means will help to ensure that it is available when needed and that it will function properly in an emergency. Furthermore, it is crucial to understand the implications of Article 100 in the National Electrical Code, which defines readily accessible. Readily accessible means capable of being reached quickly for operation, renewal, or inspections without requiring those to whom ready access is requisite to climb over or remove obstacles or to resort to portable ladders, and so forth. This definition should be carefully considered when determining the location of the disconnecting means to ensure compliance with the National Electrical Code. Let's also consider the specific requirements outlined in Section 225.31, which states that means shall be provided for disconnecting all ungrounded conductors that supply or pass through the building or structure. This section emphasizes the need to disconnect all ungrounded conductors, ensuring that the entire electrical supply can be isolated for safety purposes. Furthermore, Section 225.33 addresses the type of disconnecting means required, stating that the disconnecting means shall be installed at a readily accessible location either outside of the building or structure or inside nearest the point of entrance of the conductors. This requirement provides flexibility in locating the disconnecting means while ensuring accessibility for operation and maintenance. Now let's discuss the importance of coordination between the overcurrent protection device at the main switchboard and the disconnecting means at the distribution panel. Coordination ensures that in the event of a fault, only the overcurrent device closest to the fault will trip, minimizing the disruption to the electrical system. This is achieved by carefully selecting the ratings and characteristics of the overcurrent devices so that they operate in a coordinated manner. A coordination study should be performed by a qualified electrical engineer to determine the appropriate settings for the overcurrent devices. The coordination study should take into account the characteristics of the electrical system, the load requirements, and the potential fault currents. Proper coordination will help to ensure the reliability and safety of the electrical system. In addition to coordination, it is also important to consider the voltage drop in the feeder conductors. Voltage drop is the reduction in voltage that occurs as electricity flows through a conductor. Excessive voltage drop can cause equipment to malfunction and can also reduce the efficiency of the electrical system. The National Electrical Code provides guidelines for calculating voltage drop. Section 215.2A3 recommends that the voltage drop on feeder conductors should not exceed 3%. It is important to select the appropriate size conductor to minimize voltage drop. The conductor size should be based on the load requirements, the length of the feeder, and the allowable voltage drop. Furthermore, it is important to consider the ampacity of the feeder conductors. Ampacity is the maximum amount of current that a conductor can carry safely without overheating. The National Electrical Code provides tables that list the ampacity of various conductors. The ampacity of the conductor should be based on the load requirements and the ambient temperature. It is also important to consider the dirting factors that may apply to the conductor ampacity. Dirting factors are used to reduce the ampacity of a conductor when it is installed in certain conditions, such as in a conduit with other conductors or in a high ambient temperature. In the context of hospitals, it is imperative to recognize the unique criticality of their electrical systems. Hospitals rely on a continuous and reliable power supply to support life-saving equipment, critical care units, and other essential services. Any interruption to the electrical supply can have serious consequences, potentially endangering patient lives. Therefore, the design, installation, and maintenance of electrical systems in hospitals must adhere to the highest standards of safety and reliability. This includes implementing redundant systems, backup power sources, and rigorous testing and maintenance procedures. The disconnecting means should be selected and installed with careful consideration of its impact on the overall reliability of the hospital's electrical system. Furthermore, it is important to comply with the specific requirements for essential electrical systems in hospitals, as outlined in Article 517 of the National Electrical Code. Article 517 provides detailed requirements for the design, installation, and testing of essential electrical systems in healthcare facilities. These requirements are intended to ensure that essential services such as lighting, medical equipment, and communication systems are provided with a reliable source of power in the event of a power outage. It is imperative to consult with a qualified electrical engineer and electrician who are experienced in healthcare electrical systems to ensure compliance with Article 517 and other applicable codes and standards. The essential electrical system typically consists of two or more independent power sources, such as a normal power source and one or more emergency power sources. The emergency power source is typically a generator or an uninterruptible power supply UPS. The essential electrical system also includes transfer switches, which automatically switch the load from the normal power source to the emergency power source in the event of a power outage. The transfer switches must be designed and installed to ensure a reliable and seamless transfer of power. The essential electrical system must be tested regularly to ensure that it is functioning properly. The testing should include a load test, which simulates a power outage and verifies that the emergency power source can carry the essential loads. The testing should also include a transfer test, which verifies that the transfer switches are functioning properly. The testing should be performed by a qualified electrical engineer or electrician. In summary, when installing a feeder to a separate building in a hospital setting, it is essential to consider the unique requirements and criticality of the electrical system. Compliance with the National Electrical Code, Article 517, and other applicable codes and standards is paramount. Consulting with qualified professionals and implementing robust design, installation, and maintenance practices will help to ensure the safety and reliability of the hospital's electrical system. Let's delve into specific scenarios and how the NEC addresses them. Imagine a situation where the feeder runs underground for most of its length but enters the building above ground for a short distance. In this case, the 25-foot rule from exception number 1 might become relevant. If the feeder enters the building in a raceway and the length of the raceway inside the building is no more than 25 feet, the disconnecting means might not be required at the building entrance, provided the other conditions of exception number 1 are met, such as having overcurrent protection on the premises. However, it's crucial to meticulously measure the raceway length and ensure strict compliance with the 25-foot limit. Now let's consider a scenario where the hospital building houses sensitive medical equipment that requires a highly stable and uninterrupted power supply. In this case, the disconnecting means might need to be designed to minimize any voltage fluctuations or transients during switching. This could involve using specialized disconnecting switches with features like soft switching or surge suppression. Furthermore, the location of the disconnecting means should be carefully chosen to minimize the impact on the sensitive equipment. For instance, it might be preferable to locate the disconnecting means closer to the main switchboard in the originating building to isolate any disturbances from the sensitive equipment. Another aspect to consider is the potential for future expansion or modifications to the electrical system. The disconnecting means should be sized and located to accommodate any anticipated future load increases or changes in the building's electrical configuration. This could involve installing a larger disconnecting switch than currently required or leaving space for additional disconnecting switches in the future. It's also important to maintain accurate and up-to-date documentation of the electrical system, including the location and characteristics of the disconnecting means. This documentation should be readily available to qualified personnel for maintenance, troubleshooting, and future modifications. The documentation should include detailed drawings, specifications, and testing records. Regular training should be provided to qualified personnel on the operation and maintenance of the electrical system, including the disconnecting means. This training should cover topics such as safety procedures, troubleshooting techniques, and preventive maintenance practices. Furthermore, it's important to consider the impact of the disconnecting means on the overall energy efficiency of the building. The disconnecting means should be designed to minimize energy losses and to optimize the performance of the electrical system. This could involve using energy-efficient disconnecting switches or implementing strategies such as load shedding to reduce energy consumption during peak demand periods. Let's consider a scenario where the hospital has a centralized emergency power system that serves multiple buildings. In this case, the disconnecting means might need to be coordinated with the emergency power system to ensure a seamless transfer of power during a power outage. The disconnecting means should be designed to prevent any backfeed of power from the emergency power system to the normal power system, which could damage equipment or create a safety hazard. The disconnecting means should also be designed to allow for manual switching between the normal power system and the emergency power system in case of a failure of the automatic transfer switch. Now, let's discuss the importance of arc flash hazard assessments in the context of disconnecting means. Arc flash is a dangerous electrical explosion that can occur when there is a fault in the electrical system. Arc flash can cause serious burns, injuries, and even death. An arc flash hazard assessment should be performed to determine the potential arc flash hazard at the disconnecting means. The arc flash hazard assessment should take into account the voltage, current, and clearing time of the overcurrent protective device. Based on the arc flash hazard assessment, appropriate personal protective equipment (PPE) should be selected for personnel who may be working on or near the disconnecting means. The PPE should include items such as arc-rated clothing, gloves, and face shields. Warning labels should be placed on the disconnecting means to alert personnel to the potential arc flash hazard. The warning label should include information such as the arc flash boundary, the incident energy, and the required PPE. In addition to PPE and warning labels, it is also important to implement safe work practices to minimize the risk of arc flash. These safe work practices should include procedures such as energizing the equipment before working on it, using insulated tools, and maintaining a safe distance from energized equipment. Regular training should be provided to personnel on arc flash hazards and safe work practices. Furthermore, it's important to consider the grounding and bonding requirements for the disconnecting means. Proper grounding and bonding are essential for preventing electrical shock hazards and for ensuring the proper operation of the electrical system. The disconnecting means should be grounded to a common grounding electrode system. The grounding electrode system should consist of a grounding electrode, such as a ground rod or a metal water pipe, and a grounding conductor that connects the grounding electrode to the electrical system. The disconnecting means should also be bonded to all metal enclosures and equipment. Bonding is the process of connecting metal parts together to create a low impedance path for fault current. Proper grounding and bonding will help to ensure that the electrical system is safe and reliable. It is important to comply with the grounding and bonding requirements of the National Electrical Code, which are outlined in Article 250.